Everyone. This little video is called Token Distributions because we're going to talk about pulling a token out of a jar and getting 3 red tokens in a row. It's an example of a discrete random probability distribution. Discrete random probability distribution. So let's jump into it. So the scenario is inside this jar there's 7 green, 7 red and 7 blue tokens, 21 tokens altogether, 3 different colors, same number of each of them, right? So just to illustrate that, here we go. Let me shake them up and show you they're all there, 7 of each. Excellent. So this is what I do next. I put my hand in and I pick out what we got. There's a green. Pick another one. There's a red. And pick another one. Awesome, there's a blue. Okay, so green, red, blue. What's the chances of that happening? And more importantly, to win, I need 3 reds. So what's the chance of that happening? Well, because there are the same number of tokens of each color in there, and because I replace it every time, there's going to be 27 equally likely outcomes. 27 because there's 3 possible results, and you do the trial 3 times. So 3 to the power 3, 27. And all of them are equal likely because there's the same number of tokens as for each color every time. Okay, so what we can do is rewrite that into a probability distribution, talking about the number of reds. So you could have 3 reds, 2 reds, 1 red, or no reds. Okay, how are we going to work this out? Well, one way is get your probability distribution, trace along the line, say, oh, okay, red, 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 and then trace along the row, red, red, green, red, red, blue, and list out all the things, and then let's highlight them. So there's 3 reds up here. The yellow color shows you, well, there's 2 reds, green color shows you 1 reds, purple color, there's no reds at all. Okay, then I count them up, and then I can put them in my table. And I double check here, 18 plus 12 is 20, plus 6, 26, plus 1, 27. 27 out of 27, yeah, 1. It is certain that I will get one of these 4 results. Okay. Now you're saying to me, you're kidding, right? I've got to do all that work. I've got to do a whole tree diagram, write all this out, got to highlight all these different colors. It's annoying. Is that really what I need to do? Isn't there a magic formula you can tell me? Well, ladies and gentlemen, yes, there is a magic formula, but I'm not going to tell you it yet. We're going to discover it for ourselves. Okay? So, when you say there's no reds, that means you're going to get not red, and not red, and not red. Okay? If 1/3 are red, then 2/3 are not red. So it'll be 2/3 times 2/3 times 2/3. Right? Whenever you say and in probability, that's a multiply. So 2/3 times 2/3 times 2/3. Okay, now to get 1 red, there's 3 ways that can happen. Hold on, this says 12. What do you mean 3? Well, what I mean is you can get red and then not red, or, when you say or, there's a plus, not red, red, not red, or not red, red. So there's 3 ways it can happen. 2 of them, the 2 of the picks are not red, and 1 of the picks is red. Okay, so it's 3 times probability of not red squared times probability of red. And getting 2 reds is really similar to this, because this time you'll have 3 ways of getting 1 not red and 2 reds. Okay, red, red, not red, not red, not red, red. There's 3 ways. So it's 3 times the probability of not red times the probability of red times the probability of red. Okay, and how do you get 3 reds? The only way is red, red, red. So it's 1/3 times 1/3 times 1/3. So there's our magic formula. And we'll learn more about that later on and in some of the other videos I've linked below. But if you can do that from your logic, it's much better than memorizing a formula. Okay, now you're probably thinking, hey, this is a dumb game where I have to put the tokens back every time. Can't I just keep the tokens out? Do I have to replace them? What if I don't replace them? Well, you still use the same formula, but this time the probability changes every time. So if you wanted to get 3 reds, the chance of getting the first one red is 7 out of 21. But now there's 20 tokens left and only 6 of them are red. So the probability for the second draw is 6 out of 20. And then you've got 5 out of 19 on the third draw. So that all cancels out and works out to 1 on 38. And can I do something similar for the rest of the distribution? Yes, you can. So again, this is here for 0 reds, it's not red, not red, not red. For 1 red, there's 3 ways of getting red, not, not. And for 2 reds, there's 3 ways of getting red, red, not. And then this is what we just worked out up here. And again, if you add up all these decimals here, you'll get 1. Okay, awesome. So that's basically everything you need to know about discrete probability distributions. Actually, this one we've talked about is a binomial distribution because we've got red and not red, but that's another story for another time as well. But that's how you work out discrete random probability distributions. I'll give you one more example. I'm going to change the rules of my game. This time you win, it's not just 3 reds that wins, it's 3 of anything. So let's talk about the probability of multiples. And let's just do with replacement to keep the numbers simple. This time there's no 1 here because you can have 3 that are the same color, 2 that are the same color, or they're all different. So all different, I could call that 1, I could call that 2. I could call that 0. Let's call it 0, it makes more sense to me. Okay, so let's, again, we could go from the tree diagram. And you see there's 3 out of the 27 that are triples, and we'll color in those. So there's 18 out of 27 that are doubles, and the rest are singles. So 6 plus 18 plus 3 equals 27, 27 out of 27, good. That's everything. So I did that by looking at the tree diagram. Is there a formula for this? Well, it's not as easy, but yes, there is. Okay, so here's the thinking. The first one, it doesn't matter what you pick the first time. So you don't have to write this. A lot of people don't. I write it because it helps me remember what I'm doing. Doesn't matter what you pick the first time. So you pick any 3 out of the 3. Then the next one has to be different to that. So it's a 2 out of 3 chance. And the third one has to be different to the first 2. So there's a 1 out of 3 chance of that happening. Okay. 2 tokens of the same color, 1 different. There's actually 3 ways we can do that. Doesn't matter what the first one is, but the next one's got to be the same, and then the third one's got to be different. Or, doesn't matter what the first one is, the second one's different, and the third one is the same as the original one. Or, doesn't matter what the first one is, the second one has to be different, and the third one's the same as the second one. Okay? So there's 3 ways here. same, different, same, 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 different, and different, same, same. I said that wrong. No, I said that right. Okay, and then last one is 3 tokens of the same color. Well, it doesn't matter what the first one is. Just the second one's got to be the same as it, and the third one's got to be the same as it. So again, that's 1/9. So there you go. There's some good, challenging, discrete, random variables put into probability distributions. Okay, hope this helps you with thinking about this concept and doing some more examples yourself. Good luck.